Hello, everybody. I would like to talk about our investigation on the fracture of 3D printed parts. Our research is entitled Effect of Geometry and Thermal Aging on the range of 3D printed polymer parts. This presentation is prepared for the third European Conference on the Structural Integrity of Additively Manufactured Material. This research has been performed in the Institute of Product Development at the University of Siegen in Germany. This presentation includes introduction, which covers a brief overview of 3D printing technology, materials which are currently used in this manufacturing process, advantages and limitation of 3D printing. Then I will continue by the experimental test, where I will describe specimen preparation, details of thermal aging, mechanical test, and the obtained results. The last part of this talk would be a short conclusion. Additive manufacturing or 3D printing is a manufacturing process which involves the physical fabrication of an object from a digital model by binding thin successive layers to build up the final shape. American Society for Testing and Material and also International Standard Organization define 3D printing as a process of joining materials to fabricate parts from the 3D model data. As you can see, they also classify 3D printing into 7 processes, which are binder jetting, material extrusion, direct energy deposition, material jetting, sheet lamination, powder bed fusion, vat photopolymerization, as is illustrated in this slide. 3D printing was introduced in the last century, and advances in 3D printing have stimulated the interest of the research community, as evidenced by the increasing number of the scientific works on the 3D printed parts published in the recent years. Lack of comprehensive information about the effect of thermal aging on the fracture and mechanical behavior of 3D printed polymer with different geometry can be considered as a motivation of this research. Here we present some main advantage and limitation of additive manufacturing based on the utilized technique. 3D printing is a fast process which has positive impact on the environment. Moreover, high accuracy and the reduction in the material usage are benefits of 3D printing technology. In different 3D printing process, multiple material can be used in one component, which is advantage compared to the other manufacturing processes. High accuracy and reduction in the material usage are also benefits of 3D printing technology. On the other hand, 3D printers are not large enough. Therefore, part size is one of the existing limitations in 3D printing. Moreover, different components require post-processing, and most 3D printed parts need some form of the cleaning up to remove support materials from the build, and this can be considered as a limitation in 3D printing. As already mentioned, material extrusion is one of the main methods of 3D printing. Fused deposition modeling, or FDM, is an example of material extrusion process. In the FDM, as you may know, the melt extrusion method is used to deposit filament of the thermoplastic according to the specific pattern. In this figure, a schematic of 3D printing based on the FDM process is illustrated. In the FDM process, different printing parameters can be defined and changed. For instance, printing speed, layer thickness, nozzle temperature, and air gap can be defined with desired values. In this slide, 3 parameters are listed: raster angle, printing speed, and infill density. For example, printing speed is the distance traveled by the extruder along the bed per unit time. However, it is often difficult to control all printing parameters together. And let's go to the second section, which presents detail of the experimental test. In preparation of the specimen, here we use this. Here we designed the specimen with 3 geometries we call dog bone, smooth, and V-notch. All specimen printed with the raster direction plus minus 45 degrees, and by the definition, raster direction is the printing direction relative to the loading direction. In the figure, you can see the details of the printing in a dog bone shaped specimen. In this slide, you can see 3D printed specimens and their details. As it's shown, the length and the width are 150 and 15 millimeter, which are equal in all specimens, in dog bone, smooth, and V-notch. Here, printing parameters such as nozzle temperature, printing speed, infill percentage, and layer thickness are summarized in a table. For example, bed temperature was 55 centigrade degree, and we use a nozzle with a diameter of 0.4 millimeter in fabrication of the specimen. It should be noted that printing parameters were kept constant in fabrication of all specimens. In the current study, we printed 14 specimens for each geometry, and half of the specimens were subjected to the accelerated thermal aging. After printing process, the samples were kept at the room temperature for 1 day, and then half of the specimens in each geometry were subjected to the accelerated thermal aging. To this aim, we use environmental climate test chamber, and the specimens were artificially aged in the temperature range of -5 to +35 centigrade degree. Each temperature was kept for 1 hour, and aging duration was 10 days. In this figure, you can see specimens inside the test chamber. After accelerated thermal aging, all aged and unaged specimens were subjected to the tensile test. For the tensile test, we use a hydraulic machine which was subjected with 15 kilonewton load cell, and all tensile tests were carried out at the rate of 5 millimeter per minute. The hydraulic operated RAM with the computerized recording facility provides load deflection curves for each sample till it breaks. And in this slide, you can see a specimen under test condition. A series of tensile tests on the aged and unaged specimen were performed under laboratory condition, and repeating the test on each group of the specimens and obtaining similar results confirm repeatability of the test. Here you can see the fractured specimen with different geometry, and in this experimental test, brittle fracture was observed in all specimens, dog bone, smooth, and V-notch. In order to quantify the influence of thermal aging on the mechanical behavior of the specimen, the load deflection curves of aged and unaged specimens with different geometry were obtained, which are shown here in figure 9. Based on the obtained result, thermal aging on the specimens has led to decrease in the failure load. The applied tensile load is increased almost linearly, you can see in the curves, according to the specimen stiffness. Tests indicated that the unaged smooth specimens showed the highest failure load, and the lowest failure was belonged to the aged dog bone specimen. Moreover, experiments confirmed that the conducted accelerated thermal aging lead to decrease in the strength and stiffness of the components. You can see the values from the experimental test. The conducted test also showed that there is a sudden failure in the specimen, and all groups of the specimens are not plastically deformed during the test. As a short conclusion, I would like to review the presentation briefly. First of all, additive manufacturing and advantages of this manufacturing process were described. In the second section, details of a specimen preparation was presented, where we used the FTM technique for fabrication of the specimen. In description of the experimental test, details of accelerated thermal aging and series of tensile tests are explained. Finally, as a result, we have demonstrated force displacement curves of aged and unaged specimen with different geometry, which show accelerated thermal aging can lead to decrease in the strength of 3D printed components. Thank you very much for your attention, and let me know if you have any questions.